Half the ordinary matter in the universe is simply gone. We are made of atoms, the same kind of stuff that forms stars and planets. Yet when cosmologists take a cosmic inventory, they find only about half of what their calculations say should exist. This is the Missing Baryon Problem, one of the biggest unsolved puzzles in modern science. It is not about the mysterious dark matter, but about the very normal atoms that are supposed to be right here, and yet they have vanished from our view. Solving it is like the ultimate detective story, where the clues are scattered across billions of light years. By the end of this, you will understand the 25 brilliant methods scientists are using to track down this missing half of all normal matter. We will see how the universe hides an entire ocean of matter in plain sight and question what it means that the fabric of our reality is still full of secrets. What do you think it would mean to find something that makes up half of everything? The story of this cosmic disappearance begins with a single, undeniable number. From the faint whisper of the cosmic microwave background, the afterglow of the Big Bang itself, we can weigh the entire universe. This ancient light tells us precisely how much ordinary matter, the stuff of atoms, should exist. We call this matter baryons, which is just the scientific term for protons and neutrons, the building blocks of everything you see and touch. This measurement is incredibly precise, a cornerstone of our cosmic model. Yet when astronomers add up everything they can actually see, everything they can point a telescope at, the total comes up staggeringly short. They count the brilliant galaxies, the swirling nebulae, the vast clouds of cold gas between the stars. They tally every star in every corner of the observable universe, and still the sum is only about half of what that primordial echo says should be there. It is not a small rounding error, it is a deficit of epic proportions, a gap in our understanding as vast as the cosmos itself. This is the heart of the mystery, the first and most fundamental clue. We are not looking for some exotic, unknown substance like dark matter. We are searching for the atoms we know and understand, the very fabric of our own existence, and they have simply vanished from view. The universe, it seems, is hiding half of itself in plain sight. So where do you even begin to search for an ocean of missing atoms? The second clue comes not from looking at the light we see, but from studying the light that gets taken away. Astronomers turned their gaze to the most brilliant beacons in the distant cosmos, quasars. These are the furious hearts of ancient galaxies, powered by supermassive black holes, shining with the intensity of 1 trillion suns. Their light travels for billions of years to reach us, and on that unimaginable journey, it passes through every corner of the universe. It is this epic voyage that provides our first real map of the hidden world. As the quasar's intense ultraviolet light streams through space, it encounters vast, diffuse clouds of hydrogen gas, the most basic element in existence. When the light hits a hydrogen atom, it can be absorbed at a very specific fingerprint wavelength known as the Lyman Alpha line. But the universe is expanding, so each cloud of gas is moving away from us at a different speed. This stretches the light, shifting that absorption fingerprint to a slightly different place in the spectrum. The result is breathtaking. Instead of seeing a single absorption line from one cloud, the spectrum of a distant quasar reveals a veritable forest of lines. Each thin, dark line in this Lyman Alpha Forest is a bookmark, marking the presence of a specific cloud of hydrogen at a specific distance along the line of sight. It is a cosmic barcode, and by reading it, scientists can create a three-dimensional map of the otherwise invisible gas that fills the space between galaxies. This fog of hydrogen is our prime suspect. It is not in nice, neat galaxies. It is spread out in a vast, tenuous web, so diffuse that it emits almost no light of its own, yet so pervasive that it could easily account for a huge portion of the missing baryons. The forest tells us the hidden matter is there, woven into the very fabric of cosmic space. but mapping the forest of hydrogen only reveals the cooler, denser strands of this cosmic web. To find the truly massive reservoirs of missing matter, we must venture into a far more extreme environment. This brings us to the third clue, and the current leading suspect in the case, the warm-hot intergalactic medium, or the WIM. Picture the universe not as a collection of isolated islands, but as a single, vast, interconnected ocean. In this analogy, galaxies are merely the froth on the waves, while the real volume, the deep water, is an immense and seething network of gas. The WIM is that ocean. It is a superheated plasma, a soup of protons and electrons stripped from their atoms, threaded along the filaments of the cosmic web. Its temperature is staggering, reaching millions of degrees, yet it is so fantastically diffuse that a cubic meter of it might contain only a single atom. This combination of extreme heat and extreme thinness makes it nearly invisible. It is too hot to glow in the familiar light of stars, but too cool and spread out to shine brightly in the high-energy X-rays we typically use to find hot gas. It exists in a frustrating observational shadow, a ghost in the machinery of the cosmos. Yet theory tells us this ghost must be real. The gravitational pull of dark matter sculpted the universe into a web-like structure, and ordinary matter, the baryons, flowed into those channels. As it crashed together in these vast cosmic rivers, it heated up to incredible temperatures. The WIM is not a side effect. It is the predicted main repository for the missing half of all normal matter. Finding it is not just about spotting a cloud, it is about proving we understand the fundamental architecture of everything. The ghostly WIM may be nearly invisible, but it is not completely silent. To hear its faint whisper, we must listen in a different part of the cosmic spectrum, one far beyond the light our eyes can see. This is the realm of X-rays, where the universe reveals its most energetic and violent processes. Our fourth clue comes from two magnificent observatories, the Chandra X-ray Observatory and XMM Newton, which have become the premier detectives in this high-energy hunt. They are not looking for the WIM to glow brightly, for it is too tenuous for that. Instead, they employ a clever trick of subtraction. They train their sensitive instruments on the brightest X-ray sources they can find, often the seething atmospheres of massive galaxy clusters. As that intense background X-ray light travels across billions of light years to reach us, it passes through the filaments of the cosmic web, and there, within the WIM, something critical happens. The superheated gas is not just a soup of protons and electrons. It contains traces of heavier elements like oxygen, forged in the hearts of ancient stars and scattered across the cosmos by supernova explosions. In the million-degree heat of the WIM, this oxygen is stripped of most of its electrons, becoming what scientists call highly ionized. Atoms in this state have a very specific appetite. They absorb X-ray light at precise fingerprint wavelengths. So astronomers point Chandra and XMM Newton at a brilliant X-ray source, and they meticulously dissect the light that arrives. They are searching for tiny, telltale dips in the signal, faint absorption lines that correspond to ionized oxygen, specifically O7 and O8. Finding these lines would be the smoking gun, definitive proof that the warm-hot intergalactic medium is real, and that it contains a significant portion of the universe's normal matter. There have been landmark studies, moments of great excitement, where teams analyzing data from these telescopes believed they had found these elusive signatures. They reported faint dips in the X-ray spectra that aligned perfectly with the predicted fingerprints of oxygen in the WIM, seemingly tracing the vast, hidden rivers of gas between galaxies. Yet confirmation has been maddeningly difficult. The signal is extraordinarily weak, dancing at the very edge of what these powerful telescopes can detect. Distinguishing it from instrumental noise or other cosmic backgrounds is a monumental challenge. Each potential detection is met with rigorous scrutiny and often debate. This ongoing struggle highlights just how elusive this missing matter truly is. hiding in a realm that pushes our greatest technologies to their absolute limits. The search for the WIM faint signature demands not just looking at light, but observing how light itself is subtly changed by its journey. A fifth brilliant clue comes from using the oldest light in the universe as a cosmic backlight. We are talking about the cosmic microwave background, that faint, cold glow from the dawn of time that permeates every corner of space. Imagine this ancient radiation as a uniform, pristine canvas of microwave light. Now picture a filament of the million-degree WIM, a river of superheated electrons lying directly in its path. As the cold CMB photons pass through this seething cloud, they do not get absorbed. Instead, they get a significant energy boost. The hot electrons scatter the photons, kicking them to slightly higher energies in a process known as inverse Compton scattering. This interaction leaves a unique telltale stamp on the CMB. In the direction of the WIM filament, the microwave background appears just a tiny bit warmer, while at a slightly different frequency, it appears a bit colder. This subtle, dual pattern of distortion is called the Sunyaev-Zeldovich effect, and it is a direct fingerprint of hot, diffuse gas. It does not rely on the gas being bright or containing specific elements. It only requires that the gas be hot and in the path of the CMB. This makes it a perfect tool for hunting the WIM. Teams using powerful instruments like the Atacama Cosmology Telescope in the high Chilean desert and the South Pole Telescope in Antarctica are now conducting vast, sensitive surveys of the sky. They are not looking for galaxies or stars. They are meticulously scanning for these minuscule, characteristic distortions in the cosmic microwave background, searching for the shadowy imprints left by the warm, hot intergalactic medium as it scatters the universe's oldest light. Finding a clear SZ signal from the cosmic web filaments would be a monumental achievement, a way to weigh the hidden gas directly and finally confirm that these predicted reservoirs hold the missing baryons. It is a patient statistical hunt, piecing together a map of the invisible from the faintest of whispers imprinted on the first light of creation. The faint whispers of the cosmic microwave background are not our only backlight. A sixth and spectacularly powerful clue has exploded onto the scene from the most energetic events in the modern universe, fast radio bursts. These are not gentle signals. They are catastrophic flashes, brief blasts of radio waves that for a single millisecond outshine entire galaxies, and they come from billions of light years away. Their origin is still a mystery, involving magnetars or cataclysmic stellar collisions, but for cosmologists they are a gift. They act as the ultimate cosmic lighthouses. When one of these incredibly bright, short pulses begins its journey across the universe, its light is pristine and compact, but as it travels, it passes through the diffuse sea of electrons in the WIM and other intergalactic plasma. This encounter does something fascinating. It slows the light down, not all at once, but in a way that depends on its wavelength. The lower frequency radio waves get delayed slightly more than the higher frequency ones. By the time the burst signal finally reaches our telescopes, what was a sharp spike has been stretched out into a distinctive descending chirp. The degree of this dispersion, the amount of that stretch, is a direct measure of the total number of free electrons the signal encountered on its epic journey. And since those electrons come from ionized hydrogen and helium, the basic atoms of ordinary matter, measuring the dispersion gives us a direct tally of the total baryons along that specific line of sight. Each fast radio burst is like a single, brilliant probe fired through the darkness, and the smear of its signal paints a precise picture of the invisible material it traveled through. This new tool provides a completely independent check on the other methods. By collecting data from many bursts coming from different distances and directions, astronomers are beginning to build a statistical map of the missing matter's distribution. The early results are tantalizing, suggesting that the numbers are adding up, that the combined density of electrons in the cosmic web could indeed account for the missing half. It is a revolutionary way to see the unseen, using the universe's most violent flashes to illuminate its quietest, most hidden depths. While fast radio bursts illuminate the path with brilliant flashes, there is another, more subtle messenger traveling the cosmic web. Our seventh clue arrives not as light, but as a relentless rain of atomic shrapnel from deep space, cosmic rays. These are not rays at all, but atomic nuclei, protons and heavier elements, accelerated to nearly the speed of light by supernova explosions or the jets of active galaxies. They travel for millions of years, zigzagging through magnetic fields until a tiny fraction finally slams into our atmosphere. But their journey holds a secret map of the spaces they crossed. As a high-energy proton, a cosmic ray, barrels through the vast, near emptiness between galaxies, it has a very small but real chance of colliding with a proton just floating there in the whim. This is not a gentle bump. When two protons collide at such fantastic speeds, they can create a shower of secondary particles, including high-energy gamma rays. The probability of this happening depends directly on how much stuff is in the way, the density of the intergalactic medium. So by carefully measuring the number and energy of cosmic rays that reach us, and by searching for the diffuse glow of gamma rays that these collisions should produce across the sky, astrophysicists can work backwards. They can calculate the total amount of baryonic material these cosmic rays must have passed through on their epic journeys. It is a profoundly indirect measurement, like listening to the static on a long-distance radio call to guess the weather across an entire continent. The signal is incredibly faint and tangled with other sources, but it provides a crucial, independent line of evidence. It integrates over vast volumes of space, giving us a bulk measurement of the ordinary matter that fills the cosmic voids and filaments. If the density derived from cosmic rays aligns with the predictions for the WIM, it becomes another strong piece of circumstantial evidence that we are finally looking in the right place for the universe's missing atoms. Galaxies themselves hold a secret ledger, a record of mass written in the speed of their stars. For decades, the strange behavior of galaxy rotation curves became the primary evidence for the existence of dark matter. Astronomers expected that stars on the outer edges of a spiral galaxy, far from the bright core, would orbit more slowly, just as Pluto moves more sedately around the Sun than Mercury does. But observations revealed the opposite. Stars and gas clouds in the galactic suburbs whip around at nearly the same high speed as those closer in. This means there must be a tremendous amount of unseen mass, a dark matter halo, enveloping the galaxy and providing the extra gravitational grip to keep those fast-moving stars from flying off into space. This is a foundational pillar of modern cosmology, but within this same puzzle lies a more subtle clue about ordinary matter. To understand the rotation curve, you must first account for everything you can see. You tally all the baryonic mass, the glowing stars in the disk and bulge, the cold hydrogen gas clouds mapped by radio telescopes, the dust, the planets. You add it all up and plug it into your gravitational model. And here is the surprise: even before you introduce the concept of dark matter to explain the high speeds, there is often a mismatch. The observed rotation of the inner parts of the galaxy, the region dominated by visible stars and gas, sometimes suggests there should be more ordinary mass right there in the disk than our telescopes can account for. It is a shortfall within a shortfall. We have the overwhelming dark matter problem, and nestled inside it, a quieter baryonic one. This implies that a portion of the missing universal atoms might be hiding in plain sight, not in the distant cosmic web, but within the galaxies themselves, in forms we have yet to fully catalogue, perhaps as faint stars, rogue planets, or cold, dark clouds of gas that simply do not emit or absorb light in ways we have easily detected. The galaxy's own spin tells us the inventory of its visible parts is still incomplete. The silent tug of gravity within galaxies reveals another layer of the mystery, one that points to a dramatic, explosive solution. This brings us to a separate but deeply connected puzzle known as the too big to fail problem. In the pristine, cold dark matter simulations that map how our universe should have formed, a strange prediction emerges. The vast dark matter halo of our Milky Way should be swarming with dozens of sizable satellite galaxies, each held together by its own dense knot of dark matter. These clumps are massive enough, their gravitational pull so strong, that they should have easily gathered gas and formed stars, becoming bright, obvious dwarf galaxies orbiting our own. Yet when we look at the actual sky, we see only a handful. Where are all these predicted galaxies? They seem too big, their dark matter anchors too substantial to have simply failed to form stars. The leading explanation for their absence is not about dark matter itself, but about the ordinary matter, the baryons, and its extraordinarily violent behavior. Scientists propose a process called baryonic feedback. In the early, chaotic universe, the first stars to form in these small satellite galaxies were often monstrous and short-lived, exploding as supernova in a cosmic heartbeat. Later, the central black holes in these galaxies would awaken, devouring material and blasting out fierce radiation and jets. These are not gentle processes. They inject a staggering amount of energy into the surrounding gas, heating it to millions of degrees and driving powerful winds that can blow the galaxy's entire reservoir of star-forming fuel clear out into intergalactic space. This solves the too big to fail problem by preventing those dark matter clumps from ever becoming bright, star-filled galaxies we could easily see. But it does something more. It directly connects to our hunt for the missing baryons. That ejected gas, superheated and enriched with heavy elements, does not just vanish. It is hurled out into the vast corridors between galaxies, joining and enriching the very warm, hot intergalactic medium we have been searching for. So the solution to one cosmic puzzle becomes a key clue for another. The missing satellites tell a story of baryons being violently evicted from their galactic homes, forced into exile in the diffuse cosmic web, hiding in plain sight as part of the whim. The emptiness around our galaxy is not empty at all. It is the echo of ancient explosions that shaped the cosmos and scattered half of its normal matter into the shadows. Even the faintest echo can define the shape of a room. In the cosmos, the faintest echoes from the birth of time define the very architecture of reality, and they hold a precise measurement for our missing matter. This is the clue of baryonic acoustic oscillations. To understand them, we must travel back to the universe's first few 100,000 years, when it was a seething, opaque plasma of particles and light. In that primordial soup, gravity was trying to pull matter together into clumps, while the intense pressure of radiation was pushing it apart. This created a tug of war, setting up rhythmic sound waves that propagated outward through the fiery medium. These were literal sound waves in the early universe, spherical ripples of overdensity moving at a significant fraction of the speed of light. Then, in an instant, everything changed. The universe expanded and cooled enough for atoms to form, suddenly becoming transparent. The light, which had been trapped, burst free in every direction, carrying with it a snapshot of those frozen sound waves. That light is the cosmic microwave background we see today, and its subtle temperature variations are the imprint of those ancient oscillations. Crucially, the waves could only travel a specific distance before the universe became transparent. That distance became a standard ruler etched onto the fabric of space, a cosmic yardstick about 500 million light-years across. Fast forward billions of years. Gravity has taken those tiny initial overdensities and amplified them into the vast cosmic web of galaxies and clusters we see today. And because galaxies preferentially form from those initial seeds, they inherit the pattern. Galaxies today are slightly more likely to be separated by that specific scale, the length of that ancient sound wave, than by any other distance. This is the baryonic acoustic oscillation signal. By conducting enormous surveys like the Sloan Digital Sky Survey, mapping the three-dimensional positions of millions of galaxies, scientists can detect this preferred separation scale. It acts as a perfect calibration tool because we know the true physical size of that standard ruler from the physics of the early universe. We can measure how it appears stretched or compressed in our surveys. This tells us with phenomenal precision how the universe has expanded over cosmic time, which in turn constrains the total density of all matter and energy. Here is where the hunt for missing baryons gets a crucial number. The BO measurements give us a very tight constraint on the total matter density, including both dark matter and ordinary baryons. We already have excellent, independent measurements for the dark matter density from other cosmic probes. We also have a good tally for the baryons locked in stars and cold gas. So we take the total matter number from the BAO, subtract the dark matter, subtract the visible baryons, and what is left is a number, a precise quantity of ordinary matter that must exist but is not in our direct inventory. It is the size of the gap. The baryonic acoustic oscillations do not tell us where the missing atoms are hiding, but they tell us, with unshakable confidence derived from the first sounds of the cosmos, exactly how much we are still looking for. The universe's own infancy provides the ledger against which all our searches are measured. The ancient light of quasars reveals more than just the wispy fog of the cosmic web. Within that forest of absorption lines, astronomers sometimes stumble upon something far more substantial, a line so deep and dark it stands out like the silhouette of a giant sequoia against a misty backdrop. These are the damped Lyman Alpha systems, and they represent clue number 11 in our cosmic investigation. Think of the diffuse Lyman Alpha Forest as a widespread, tenuous mist filling the universe. A damped Lyman Alpha system, in contrast, is a dense, compact cloud, a veritable thunderhead. The name itself tells the story, damped, meaning the absorption line is so strong it completely saturates. It soaks up all the light at that specific wavelength. This only happens when the cloud of intervening gas is incredibly rich in neutral hydrogen, atoms that have not been stripped apart by intense radiation. These are not hot, ionized filaments. They are cold, dark, and massive reservoirs of pristine fuel, often containing more hydrogen than an entire galaxy like our Milky Way. In many ways, they are cosmic construction sites caught in a specific moment, vast clouds of gas that have not yet fully collapsed to form the brilliant stars of a mature galaxy. They are the progenitors, the raw material from which future galactic disks will coalesce. When we find one, we are looking at a galaxy in its infancy, a snapshot of creation before the first major burst of starlight. And because they are so dense, each one holds a staggering amount of ordinary matter. Cataloging them has been a major effort, using thousands of quasar spectra to hunt for these deep, dark lines across cosmic time. The result of this meticulous census, however, delivers a crucial piece of the puzzle. While each damped Lyman Alpha system is a baryon treasure trove, they are simply not numerous enough. When you add up all the neutral hydrogen locked in these colossal clouds across the observable universe, the total mass, while immense, still falls far short of accounting for the missing 50%. They are a major component, a significant chapter in the story of cosmic matter, but not the final answer. Their existence tells us that a portion of the missing atoms are indeed tied up in these cold, dark galactic nurseries, yet the majority must still be elsewhere, waiting in the hot, diffuse embrace of the intergalactic medium. Zooming in from the vast cosmic web, we find a hidden ocean clinging to every galaxy like a seething, extended atmosphere. This is the circumgalactic medium, and it may hold more ordinary matter than all the stars within the galaxy itself. Picture our Milky Way not as a flat disk of stars in empty space, but as a brilliant island embedded within a colossal, spherical halo of million-degree gas. This hot atmosphere stretches for hundreds of thousands of light years, a dynamic interface where the galaxy meets the void. It is fed by two powerful cosmic currents. From above, pristine gas from the intergalactic medium rains down in a gentle inflow, the future fuel for star formation. From below, violent galactic fountains erupt as supernova explosions and black hole jets blast metal-enriched gas out of the disk and into this halo. The circumgalactic medium is the crucible where these flows collide and mix, a turbulent buffer zone that regulates a galaxy's growth and evolution. For decades, it was largely theoretical, a ghostly envelope too diffuse to see. But new tools have changed everything. The Hubble Space Telescope's cosmic origins spectrograph acts like a cosmic chemical sniffer. By analyzing the ultraviolet light from distant quasars as it passes through these galactic halos, Hubble can detect the absorption fingerprints of highly ionized oxygen, silicon, and carbon imprinted on the light. Each fingerprint reveals the presence, temperature, and composition of this hot gas. Simultaneously, X-ray telescopes like Chandra peer at nearby galaxies, detecting the faint glow from the very hottest portions of these halos. Together, these observations paint a startling picture. The circumgalactic medium is not a wispy afterthought. It is a massive, complex structure containing a significant fraction of a galaxy's total baryons. This discovery forces a major revision of our cosmic inventory. We had been meticulously counting the stars and cold gas in the disks, but we were missing the immense, hot atmosphere that surrounds every single galaxy. It is as if we were trying to account for Earth's water by only measuring the rivers and lakes, while completely ignoring the oceans and the atmosphere. The circumgalactic medium is a major reservoir, a hiding place for ordinary matter that was, quite literally, right under our noses, shrouding the very galaxies we thought we knew so well. Galactic winds are not gentle breezes but cosmic hurricanes of unimaginable fury. The primary engine for these outflows is the death of massive stars. When a star many times larger than our Sun reaches the end of its life, it does not fade quietly. It explodes in a supernova, a detonation so powerful it can outshine its entire host galaxy. This is not just a flash of light, it is a cataclysmic shockwave of energy and matter. The explosion blasts the outer layers of the star, now fused into heavy elements like oxygen, carbon, and iron, out into space at speeds of thousands of kilometers per second. Multiply this by millions of such explosions across a galaxy's lifetime, and you have a continuous, raging storm, but there is an even more powerful driver. At the center of most galaxies lurks a supermassive black hole. When it actively feeds on surrounding gas, it does not swallow everything. Some material is funneled into powerful, magnetically collimated jets that scream outward at nearly the speed of light, while intense radiation pours from the searing disk of infalling matter, heating and pushing gas away. This is an active galactic nucleus, and its energy output can dwarf the combined light of every star in the galaxy. Together, supernova and active black holes act as galactic-scale pressure washers. They heat vast volumes of gas to millions of degrees and drive it outward, not just from the star-forming disk, but far into the circumgalactic halo and beyond. This outflow is rich with the chemical fingerprints of stellar forges, the heavy elements that are the building blocks of planets and life. These winds do not simply dissipate. They carry their precious cargo of baryons, the very atoms that could have formed new stars. On a one-way trip into the void, the gas is ejected with such violence and heated to such extremes that it becomes almost impossible for it to cool down and fall back. Instead, it joins the great diaspora, merging with the warm, hot intergalactic medium in the vast filaments of the cosmic web. There, enriched and ionized, it becomes part of the hidden ocean, its atoms so diffuse and energetic that they slip past traditional methods of detection. The very processes that build galaxies and seed them with the elements for life are also responsible for a great cosmic exile, forcibly relocating a significant portion of the universe's ordinary matter into the darkest, most difficult-to-find places imaginable. The supermassive black hole at the heart of an active galactic nucleus is a cosmic furnace of almost incomprehensible power. While a supernova is a single, devastating blast, an AGN is a sustained billion-year inferno. Its energy does not come from nuclear fusion like a star, but from the unimaginable gravitational forces at the very edge of the event horizon. As vast rivers of gas spiral inward, they form a searingly hot accretion disk, and magnetic fields can funnel some of this material into jets that blast outward at nearly light speed, punching through the galaxy and extending for millions of light years into intergalactic space. The radiation from this process is so intense it can outshine every star in its host galaxy combined. But this is not just a brilliant light show. It is a fundamental force shaping the distribution of ordinary matter across the cosmos. The jets and radiation act like a cosmic blowtorch, directly heating the surrounding gas in the galaxy's halo and the nearby intergalactic medium to temperatures of tens of millions of degrees. This heating is a critical piece of the puzzle. For gas to collapse and form new stars, it must be able to cool down, to radiate away its energy and condense. The AGN ensures this cannot happen. It keeps the gas hot, energetic, and puffed up, effectively sterilizing it from star formation. More than that, the immense pressure from the radiation and the physical push of the jets can drive this superheated gas outward in massive winds, propelling it far beyond the galaxy's gravitational grasp. This process is a primary delivery mechanism for the warm, hot intergalactic medium. The AGN is not just a spectacle, it is a cosmic quartermaster, forcibly redistributing the universe's baryonic budget. It takes vast reserves of ordinary matter that were once concentrated in and around galaxies and scatters them into the diffuse, hard-to-detect filaments of the cosmic web. In this way, the most violent objects in the universe are directly responsible for hiding a significant portion of its normal matter, solving one mystery by deepening another. These galactic winds and black hole furnaces do not act in isolation. They weave a tapestry across the entire universe. To understand the grand pattern they create, we must step into a virtual cosmos, a reality born from pure mathematics and raw computing power. This is the 15th clue, where we witness the birth of the cosmic web not through a telescope, but inside a supercomputer. Projects like Illustris TNG and Eagle are the grand architects of this digital universe. They begin with the initial conditions of the Big Bang, a near-uniform soup of dark matter and ordinary baryons, and then they let the laws of physics play out over 13.8 billion years of simulated time. The magic and the immense challenge lies in what they include. It is not just gravity pulling dark matter into a web of filaments and halos. These simulations must also account for the fantastically complex behavior of the baryons, the ordinary matter we are made of. They model how gas cools and condenses to form stars. They calculate the explosive energy of supernova and the blistering radiation from growing black holes, the very feedback processes we just explored. They track how this energy reheats gas, drives winds, and enriches space with heavy elements. Running this cosmic recipe requires some of the world's most powerful supercomputers, crunching numbers for months to simulate a cube of space hundreds of millions of light years on a side. And when the virtual clock reaches the present day, the scientists open the box. What they see is breathtaking. A cosmic web emerges in stunning detail, with galaxies, clusters, and vast empty voids arranged just as they are in our real sky. But more importantly, these simulations give us a prediction, a theoretical map for the missing baryons. They show that a vast ocean of ordinary matter, between 30 and 50% of the total, does not reside in stars or cold gas. Instead, it is spread throughout the filaments and nodes of the web as a superheated, diffuse plasma, the warm, hot intergalactic medium. The simulations show us its temperature, its density, and even how it is enriched with oxygen and carbon blown out from galaxies. This virtual map is not proof, but it is an incredibly detailed hypothesis. It tells observers exactly where and how to look, predicting the strength of the absorption lines in quasar spectra or the subtle distortions in the cosmic microwave background. It turns the hunt from a blind search into a targeted investigation, providing the theoretical backbone that makes sense of all the other clues. In these digital universes, we watch the missing half of all normal matter hide itself, and in doing so, we get our best instructions for where to find it. The digital universes we build are haunted by ghosts, vast numbers of phantom galaxies that should exist but simply do not. This is the missing satellites problem, and it offers a profound insight into where the universe's ordinary matter might have gone. Our most sophisticated simulations of cosmic structure, driven by the relentless pull of dark matter, paint a very specific picture of a galaxy like our Milky Way. It should be surrounded by a bustling swarm of thousands of small satellite galaxies, each one anchored by its own dense knot of dark matter. These clumps are massive enough that their gravity should have easily gathered the ordinary gas needed to spark star formation, lighting them up as visible dwarf galaxies. Yet when we look at our actual cosmic neighborhood, we see only a few dozen such satellites. Where are the thousands of others? The answer lies not with the dark matter, but with the fate of the baryons within those small halos. In the early universe, before the first galaxies fully formed, a pivotal event occurred called reionization. The first generation of stars and black holes switched on, flooding the cosmos with intense ultraviolet radiation. This radiation was powerful enough to strip electrons from hydrogen atoms everywhere, reheating the intergalactic gas. For a massive dark matter halo, this was a minor setback. Its strong gravity could hold onto its gas, which would eventually cool and condense. But for the thousands of smaller, lighter halos, it was a death sentence. The incoming radiation kept their gas far too hot to ever settle down and form stars. Later, even if some gas did manage to collect, the first feeble bursts of star formation would have triggered supernova explosions, their feeble feedback enough to blow the remaining gas away entirely, as these small halos have such a weak gravitational grip. So what happened to all that ordinary matter, the baryons that were assigned to these failed galaxies? They were never able to condense into shining stars. Instead, they remained as diffuse, superheated plasma, forever suspended in a state too energetic to collapse. This gas, denied its chance to become part of a visible galaxy, was essentially donated back to the intergalactic medium. It joined the vast, hot reservoirs of the warm, hot intergalactic medium, spreading out along the filaments of the cosmic web. The missing satellites problem, therefore, is not just a puzzle about dark matter halos. It is a story of baryonic exile on a cosmic scale. It suggests that a significant population of ordinary matter was destined from the beginning to remain invisible, not in dazzling galaxies, but as part of the hidden, seething ocean that fills the spaces between everything we see. The silence of the missing satellites is in fact a loud clue pointing directly to the warm, hot, and diffuse whereabouts of the universe's missing atoms. The universe's first dawn was not a gentle sunrise, but a searing, violent flash that fundamentally changed the nature of cosmic space itself. This pivotal era, known as the epoch of reionization, began a few 100 million years after the Big Bang, when the cosmos was a very different place. After the initial glow of the cosmic microwave background faded, the universe entered a long, dark age. It was filled with a cool, neutral fog of hydrogen and helium gas, a silent and featureless expanse. Then, in the deepest voids, gravity's patient work began to pay off. The first proto-galaxies coalesced, and within them, the very first stars ignited. These were not like the stars we know today. They were behemoths, monsters hundreds of times more massive than our sun, burning ferociously hot and blue and living short, explosive lives. Their light was not the gentle white or yellow we see in the night sky. It was an intense flood of ultraviolet radiation, and this radiation possessed a specific transformative power. Each ultraviolet photon carried enough energy to strike a neutral hydrogen atom and rip its electron clean away, a process called ionization. As more of these brilliant first stars and early black holes switched on, their ultraviolet light began to eat away at the cosmic fog. Imagine a dark room slowly filling with candles, each one burning away a patch of shadow until the entire space is illuminated. That is what happened on a cosmic scale. Bubbles of ionized plasma, clear and transparent, began to grow around each source of light. These bubbles expanded and merged over hundreds of millions of years until the entire universe was reionized, transformed from a neutral fog back into a transparent plasma of free electrons and protons, the state it remains in today. This grand transformation is not just a historical footnote, it is a crucial clue in our hunt. The physics of ionization is precise. To strip the electron from every single hydrogen atom in the entire observable universe required a specific, enormous number of ultraviolet photons. And those photons had to come from somewhere. They were produced by the first stars and galaxies. By measuring how completely and how quickly reionization occurred, which we can do by studying the absorption in the spectra of the most distant quasars, we can work backwards. We can calculate the minimum number of those first luminous objects that must have existed. And since those objects were made of baryons, ordinary matter, this gives us another independent tally, another constraint on how much normal stuff was already locked up in stars and galaxies at that very early cosmic time. It tells us that a significant portion of the universal baryon budget was already hard at work, shining brilliantly, by the time the universe was only 1 billion years old. The echo of that first starlight, the very event that cleared the cosmic fog, whispers to us about the quantity and the location of matter in the infant cosmos, providing one more cross-check in our expanding ledger of the missing. The universe's first 3 minutes wrote a recipe we can still read today. In that unimaginably hot, dense beginning, protons and neutrons fused to form the lightest elements, a process called Big Bang nucleosynthesis. The amount of each element created, especially the ratio of deuterium to normal hydrogen, acts like a cosmic pressure gauge. Deuterium is a heavy form of hydrogen with a proton and a neutron in its nucleus. It is fragile, easily destroyed in the hot interiors of stars, so the deuterium we see in the cosmos today is almost entirely the pristine leftovers from the Big Bang itself. That makes it a perfect fossil. The physics of those first moments is so well understood that we can calculate precisely how the final deuterium abundance depends on one critical factor, the density of ordinary matter of baryons in the early universe. More baryons meant more collisions and more fusion, which would burn up more of the fragile deuterium. Fewer baryons would leave more deuterium behind. So by measuring the current deuterium to hydrogen ratio, we get a direct one-step measurement of the total baryon density from the dawn of time. This number is our ultimate target, the answer key to the cosmic inventory. Astronomers measure this primordial ratio by looking at the most pristine gas clouds they can find, using the absorption spectra of distant quasars to detect the faint fingerprint of deuterium in gas that has never been touched by stars. The result is a number of stunning precision. It tells us exactly how much ordinary matter the universe started with. Every other method, every tally of stars and gas and hot plasma, must eventually add up to match this primordial benchmark. It is the universe's own birth certificate, and it states unequivocally that half of the matter it lists is currently unaccounted for. This single, clean measurement from the first moments of creation is why we know beyond any doubt that the search is real. The missing baryons are not a theoretical curiosity. They are a quantitative fact written into the oldest chemistry set in existence. The most massive structures in the universe hold their own spectacular secret. When thousands of galaxies are bound together by gravity into a vast cluster, they are not floating in empty space. they are immersed in a sea of superheated plasma, the intracluster medium, and it is one of the most brilliant displays of ordinary matter in the cosmos. This gas is not lukewarm or even hot. It is searing, with temperatures soaring to tens of millions of degrees, heated to such extremes by the sheer gravitational energy released as galaxies and dark matter crashed together over billions of years. At these phenomenal temperatures, the gas is fully ionized, a soup of bare atomic nuclei and free electrons moving at tremendous speeds. And when these fast-moving electrons are deflected by the electric fields of the ions, they emit a powerful glow of X-ray radiation. This is why galaxy clusters are among the brightest X-ray sources in the sky. Through the eyes of observatories like Chandra, a cluster is not a collection of discrete points of light, but a colossal, diffuse cloud of blazing energy, a single entity where the space between the galaxies shines far brighter than the galaxies themselves. Weighing this intracluster medium is a primary goal of X-ray astronomy. By measuring the intensity and spectrum of its glow, scientists can determine its temperature, density, and total mass with remarkable precision. The numbers are staggering. In a massive cluster, the weight of this hot gas can exceed the combined mass of all the stars in all the member galaxies by a factor of 10 or more. It is a monumental reservoir of baryons, a treasure trove of the ordinary matter we have been seeking. Yet here lies the critical revelation. When cosmologists perform the ultimate cosmic accounting, adding up all the intracluster medium from every galaxy cluster in the observable universe, the total, while immense, is still not enough. It accounts for only a fraction of the missing 50%. This tells us something profound. The intracluster medium is a showcase, a demonstration of what hot baryons look like when they are concentrated in the densest knots of the cosmic web. But it is not the main hiding place. The true bulk of the missing matter cannot be solely in these spectacular but relatively rare clusters. It must be more widely distributed, more democratic, spread throughout the entire filamentary network that connects these brilliant nodes. The clusters show us the form the missing atoms take, but their scarcity tells us we must look for that same superheated state in the far more vast and tenuous spaces in between. While the classic Sunyaev-Zeldovich effect reveals the hot gas by its temperature, there is a more subtle, dynamic cousin in this cosmic toolkit. The kinetic Sunyaev-Zeldovich effect listens for motion. It searches for the gentle push of the cosmic web itself. Remember, the warm, hot intergalactic medium is not a static ocean. It is a flowing river system with vast filaments of gas streaming along the gravitational contours shaped by dark matter, falling slowly toward the dense clusters at their intersections. The electrons in this seething plasma are in constant bulk motion, and when a photon from the cosmic microwave background passes through and scatters off one of these moving electrons, something exquisite happens. The photon's frequency is shifted just slightly by the Doppler effect. It is the same principle that makes a siren's pitch change as an ambulance speeds past you. If the electron cloud is moving toward us, the scattered CMB photon gets a tiny blue shift. If the cloud is moving away, the photon gets a tiny red shift. This minuscule shift imprints a new, ultra-faint pattern on the microwave background, a pattern of temperature fluctuations that directly traces not just the presence of hot electrons, but their direction and speed. Detecting this signal is one of the most formidable challenges in modern cosmology. The expected temperature change is vanishingly small, on the order of a few millionths of a degree. It is buried under the primordial fluctuations of the CMB itself and the far stronger signal from the thermal SZ effect. To find it, scientists must use statistical cross-correlation on a massive scale. They take exquisitely sensitive maps of the cosmic microwave background from observatories like the Atacama Cosmology Telescope and the Planck satellite, and they overlay them with three-dimensional maps of where the cosmic web's filaments should be, based on the observed positions of millions of galaxies. They are not looking for a single, obvious blotch. They are searching for a consistent statistical whisper that says yes across the entire sky. The CMB is ever so slightly distorted in the precise directions where we predict flowing rivers of hot gas to exist. A clear detection of the kinetic SZ effect would be a monumental breakthrough. It would do more than just confirm the WIM existence. It would allow us to take its pulse. For the first time, we could map not just where the missing baryons are, but how they are moving. We could watch the great gravitational currents of the universe, seeing the warm-hot intergalactic medium flow into the waiting nodes of galaxy clusters, tracing the dynamic heartbeat of the cosmic web in real time. It would transform our understanding from a static inventory into a living, moving picture of how the universe distributes its most fundamental ingredient. Hubble's ultraviolet eye has been our most faithful guide into the hidden realms of ordinary matter. While other telescopes see the brilliant glow of stars or the searing heat of X-rays, the Hubble Space Telescope possesses a unique and irreplaceable gift: its ability to dissect ultraviolet light with exquisite precision. This is the domain of the Lyman Alpha Forest and the circumgalactic medium, the fingerprints of hydrogen and ionized metals imprinted on the light of distant quasars. For decades, Hubble's cosmic origin spectrograph has acted as a cosmic chemist, analyzing these faint UV signatures to map the otherwise invisible gas that clings to galaxies and threads the voids. It has given us our first real census of the cooler components of the missing baryons, proving that vast structures of ordinary matter exist in the darkness. Yet even Hubble has its limits. The signals from the hottest, most diffuse parts of the warm-hot intergalactic medium are often too faint for its instruments to catch with certainty. They flicker at the edge of detection, leaving us with tantalizing hints rather than definitive proof. This is where the next generation of explorers comes in. The future of this hunt shines with the promise of missions like NASA's proposed Reservoir, the Large UV/Optical/IR Surveyor, or the European Space Agency's Ariel. These spacecraft are designed with one overarching goal: to see the unseen with revolutionary clarity. Their ultraviolet spectrographs will be far more sensitive, able to collect light from fainter quasars and dissect it with finer detail. They will not just glimpse the WIM, they will map it. Imagine being able to point such a telescope at hundreds of distant quasars and see not just a few tentative dips in the spectrum, but a rich, detailed barcode of absorption lines from oxygen and other elements, tracing every filament of the cosmic web in vivid detail. These future observatories will transform the warm-hot intergalactic medium from a theoretical phantom into a charted territory. They will measure its temperature, its density, and how it is enriched with the elements of life across cosmic time. The patient, persistent work of Hubble has shown us the path, and soon its successors will take us the final, conclusive steps into the light. Gamma rays are the universe's most penetrating light, and their faint, omnipresent whisper holds a clue. Across the entire sky, there exists a diffuse, almost uniform sea of high-energy gamma radiation. This is not the brilliant flash of a collapsing star or the focused beam from a pulsar. It is a soft, persistent glow, a background hum that has been washing over us since the cosmos was young. Its source is a cosmic cascade of violence. Ultra-high energy cosmic rays, those atomic nuclei accelerated to nearly light speed, do not travel alone. On their epic journeys, they can collide with photons of starlight or the sparse atoms floating in intergalactic space. These collisions are so energetic they can create new particles which then decay, ultimately producing gamma rays. The intensity and the exact energy spectrum of this all-sky glow become a cosmic ledger. A denser universe with more starlight and more gas for the cosmic rays to interact with would produce a brighter, differently shaped gamma ray background. A sparser universe would leave it fainter. By meticulously mapping this diffuse glow with telescopes like NASA's Fermi Gamma Ray Space Telescope and then subtracting all the known discrete sources, scientists are left with this fundamental background. Modeling its production requires plugging in numbers for the average density of baryons, both in stars and in gas across cosmic history. It is an integrated constraint, a single number that sums up the total ordinary matter the cosmic rays must have encountered over billions of years. The measured glow is consistent with the idea that the missing baryons are out there, diffusely spread, providing just enough material for the cosmic rays to ping against on their long voyages. It is another indirect but powerful testament, a faint echo of countless invisible collisions that tells us the empty spaces are not truly empty at all. The universe's hidden oceans are not just made of hydrogen. Within the searing filaments of the warm, hot intergalactic medium, astronomers hunt for the chemical fingerprints of civilization, not our own but that of the first stellar empires. This brings us to the 23rd clue, the search for metal line absorption systems. In astronomy, any element heavier than hydrogen or helium is called a metal. When we look at the spectrum of a distant quasar, we are not just looking for the dark lines of hydrogen. We are searching for the faint, telltale dips that correspond to these heavier elements like carbon, oxygen, silicon, and iron. Finding them in the WIM would be a game changer. Hydrogen and helium are the primordial ingredients, the raw materials of the Big Bang. But carbon, oxygen, and iron, they are forged in the nuclear furnaces of stars. Their very existence in the space between galaxies tells a specific story of cosmic recycling. It means that this gas did not simply remain in the pristine void since the beginning of time. It was once inside a galaxy. It was part of the star-forming cycle, cooked into new elements within stellar cores, and then violently expelled by supernova explosions or black hole jets. When we detect a line from ionized oxygen in a WIM filament, we are not just detecting a missing atom. We are reading a history book. That atom carries with it the legacy of a star that lived and died billions of years ago. It confirms the critical link between the missing baryons and the galactic feedback processes we have discussed. The supernova winds and the active galactic nuclei are not just theoretical ideas, they are the delivery trucks. They physically transported these enriched atoms from the bright galactic disks out into the dark intergalactic highways. So finding these metals is the smoking gun that connects the dots. It proves that a significant portion of the WIM, and therefore the missing baryons, consists of processed material, gas that has been on an epic journey from the heart of a star to the emptiness between galaxies. It turns the warm, hot intergalactic medium from a theoretical reservoir into a graveyard of ancient stars, a vast cemetery where the atoms of long-dead suns now hide, holding the answer to one of cosmology's greatest mysteries. Magnetic fields weave an invisible architecture through the cosmos, a force we cannot see directly but whose influence is written in the behavior of everything it touches. This introduces our 24th clue, a layer of profound complexity to the warm, hot intergalactic medium. We have been picturing the WIM as a superheated, diffuse plasma, a simple soup of protons and electrons. But what if that soup is threaded with immense, invisible lines of force? Theorists suggest that magnetic fields, generated in the turbulent hearts of galaxies and stretched across the universe by cosmic winds, could be frozen into this intergalactic plasma. They would not be strong like a magnet on your refrigerator, but they would be pervasive, shaping the gas in subtle yet critical ways. These fields could prevent the gas from clumping too easily, acting as a kind of cosmic scaffolding that maintains its diffuse, filamentary structure over billions of years. They would also govern how heat is conducted through the plasma. In a magnetized medium, heat does not flow evenly in all directions. It travels preferentially along the magnetic field lines. This means some parts of a filament could remain hot and puffed up, while other regions might cool more efficiently, potentially creating a patchwork of slightly denser and thinner zones within the same vast structure. For observers, this is a game changer. The strength and orientation of these fields would directly affect how the gas absorbs light from distant quasars or how it scatters the cosmic microwave background. Our predictions for the telltale absorption lines of ionized oxygen depend on assumptions about the gas's temperature and density distribution. If magnetic fields are twisting that distribution, our interpretations could be off. We might be looking right at the whim but misreading its signature because we do not understand its magnetic skeleton. Unraveling this requires a new kind of cosmic detective work, searching for the faint polarization of radio waves or the subtle alignment of light that can betray a magnetic field's presence. The hunt for the missing baryons, therefore, is not just about finding the atoms. It is about understanding the complete physical state of the hidden ocean, currents, temperature, and now its invisible magnetic field. Solving the final pieces of this puzzle may depend on mapping forces we have only just begun to perceive. The final and most critical clue is not a new observation, but a new way of thinking. No single telescope, no solitary wavelength of light will ever crack this case on its own. The universe guards its secrets across the entire electromagnetic spectrum, and so our search must be just as comprehensive. This is the era of multi-messenger astronomy, the ultimate cosmic detective work where every piece of evidence must corroborate the others. Think of it as building an irrefutable case where every witness tells a different but consistent part of the same story. The radio astronomers listening for the chirp of fast radio bursts provide one measure of the total electrons along a path. The ultraviolet spectrographs, like Hubble's, map the cooler hydrogen and ionized metals in the cosmic web. The X-ray telescopes, Chandra and XMM Newton, hunt for the faint absorption lines of superheated oxygen in the warm-hot intergalactic medium. And the microwave observatories at the poles and in the desert scan for the subtle temperature distortions imprinted on the cosmic microwave background by that same hot gas. Each of these methods has its own strengths and its own frustrating blind spots. A fast radio burst gives a superb integrated measurement but poor spatial detail. An X-ray absorption line might be definitive, but it is so faint it can be lost in the noise. The ultraviolet forest maps structure beautifully but struggles with the hottest gas. The Sunyaev-Zeldovich effects are statistical, requiring vast surveys to see a pattern emerge. Alone, each clue is suggestive. Together, they are converging. The real breakthrough happens in the supercomputer labs and conference rooms where these disparate datasets are fused. Scientists take the map of galaxy positions from optical surveys and overlay the predicted locations of filaments. They then check those coordinates against the X-ray data for oxygen absorption, against the CMB maps for SZ distortions, and against the statistics of fast radio burst dispersion. They are asking one simple, powerful question: does the evidence line up? When the faint X-ray dip appears at the same redshift where a filament is predicted, and a statistical bump in the CMB aligns with that same patch of sky, and the dispersion measures from bursts that pass through that general direction agree on the density, the case becomes airtight. This cross-referencing is how we move from a tantalizing hypothesis to a confirmed discovery. It is how we will finally announce to the world that the missing half of all normal matter has been found, not in one brilliant flash, but in the quiet, consistent agreement of every eye we have trained on the darkness. The solution was never going to be a single eureka, a moment, but a chorus of whispers from across the cosmos, finally heard in unison. So the story comes together, not as a tale of loss, but of rediscovery. Our cosmic inventory was never wrong, only incomplete. The 25 clues we have followed, from the ancient whisper of the cosmic microwave background to the violent chirps of fast radio bursts, all point toward the same breathtaking conclusion. The missing half of all normal matter is not gone. It was never truly missing. It is simply hidden, woven into the architecture of the universe itself. It exists as a vast, seething ocean of superheated plasma, the warm-hot intergalactic medium threaded along the invisible filaments of the cosmic web. It clings to galaxies in massive, hot halos and flows in great rivers between the clusters. We have been searching for an ocean while standing in its midst. The mystery is now on the verge of being solved. This is not a hopeful guess, but a statement of momentum. Every new telescope, every combined dataset brings us closer. The next generation of ultraviolet observatories will map the web's chemical fingerprints in stunning detail. More sensitive X-ray missions will catch the faint absorption lines with undeniable clarity. Larger surveys of fast radio bursts and deeper probes of the cosmic microwave background will provide the statistical proof that closes the case. The multi-messenger approach, where every wavelength of light and every type of cosmic messenger tells a consistent story, is how we will finally announce the discovery to the world. This search is about more than just balancing a cosmic ledger. It is a profound reminder of our own place in this story. Every atom in your body, every element that makes up our world, was forged in stars and scattered by the very forces that hid this matter in the first place. We are literally made of this elusive cosmic stuff. To solve the mystery of the missing baryons is to complete the map of our own origins, so stay curious. Follow the new discoveries as they emerge from observatories on mountaintops and in space. Remember that the universe is still full of secrets, and the greatest ones are often hiding in plain sight, waiting only for us to learn how to see.